Welcome to video lecture on steel design. In this lecture, we will learn about LRFD design of steel columns. This LRFD refers to load and resistance factor design, and in this case there are two approaches. For design of a steel column, we will use either AISC column load tables if the sections are available, or by using trial and error if the sections are not available in these tables. These tables are given in 4.1 chapter 4 of AISC manual. First we will discuss about design with column load tables as per LRFD, which is AISC tables 4.1. So column load tables make it easy to select an economical rolled shape to resist a given compressive load. So that table is prepared for different rolled sections, which are I section, that is W section, M section, S section, T section, and you can calculate PU based on the load, and then you can determine effective length depending upon the end conditions. You can find the value of KL with respect to each axis, x axis and y axis, depending upon those restraints about x axis or y axis. Then enter the table with effective length value, which is larger of KLY or equivalent KLY, as you have seen in the previous lecture where we discuss about the design strength of column and how you know how to find effective KLY based on KLX. And then we move horizontally until the desired design strength or something slightly larger is found. So this is the step. First we find the value of PU based on the given dead load and live load, and also determine the value of KL with reference to the end conditions. We already have the value of K in that table for coefficient of effective length, and we will calculate about both axes. This is the first step. Then we will see in the table which section is referring to that value. Here, which KL value you have to take, either KLY or equivalent KLY, whichever is maximum. And our approach will be such that we select the lightest section if there are no restrictions. Sometimes there are restrictions due to some architectural requirements, so we have to take care of all those requirements. It is recommended to use column load table whenever possible because it is very easy approach. Sometimes those sections, because it is limited, it is not for every value of Fy. For Fy 50 these values are available, so we have to look for that criteria. In some cases the category of shape W, W2 etc. will have been decided upon in advance, so you have to take care of that. If the question it is given that you have to use W section or W3 section, then you are restricted only to that shape. And sometimes the overall nominal dimensions will also be known because of some architectural or other requirements. So there are also some restrictions on the size, so we have to limit that. If it says W10, W12, W8, because of the depth requirement, so we have to restrict to those values. All tabulated values correspond to a slenderness ratio of 200 or less. So that is our requirement, that we have to design a section in such a way that slenderness ratio is not more than 200, and that is maintained in these tables. Now we will see with the help of one example how we can use these tables of AISC to design a section. In this example, a compression member is to be designed for service loads of 165 kV dead load and 535 kV live load. The member is 26 feet long and pinned in each. So now the end conditions are given we can easily find what will be the effective length. Steel grade is also given as 50, so you can easily use this AISC table 4.1 and select a W14 shape. So here there is a restriction of the shape W14. So the depth is same, but the values of self weight will be different, and based on that you can select. So first step is to find PU, the design load, 1.2 times dead load plus 1.6 times live load. These are the load factors. Remember, for dead load we use load factor of 1.2, and for live load the load factor of 1.6. So when we multiply with these corresponding load factors, we get the design load as 1054 kg. So required design strength, we calculate 5 CPN, so that value will be 1054, because this design load, yes, should be according to that condition as we have seen in the previous one, because your section should be able to take this much load. It should not be less than the design load. So KL is equal to 1 into 26. You can see here length is 26 and both ends are pinned. So therefore the value of K will be 1, and we get this effective length equal to 26. Now from the column load table 4.1, for KL equal to 26 feet, and we will select a section. Now we will take you to that table and find a section. So the value of KL is 26 and the load is 1054. So we have to go to that table where W14 sections are available. Now we can see here, this is the table. Look for 26. We come here, 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 and horizontally we move until we reach at a value something like this. So this is 1230, and this is 1050, this is 956. So all these values are less. So the possibility is only for these two sections, which is W14 by 145, but it is slightly more, and this value is W14 by 132. The load capacity is 1050. Now these two are possible sections. Out of this we can select. So based on this calculation, you can say, okay, 1230 kips is more than 1054. So you can say, okay, this will be the design section. But practically, because this value for W14 by 132 is very close to 1054, because we got this value as 1050. So you can also recommend W14 by 32 for this shape. Otherwise both are acceptable for design. But if you are going to design economical section, in that case you can select this value, as practically this will not create any problem. Now we go to example 2. Here we have to select the lightest W shape that can resist a factored compressive load PU of 190 kg. So the load is defined, the design load. So it is already factored load. Dead load and live load is not separately given. The effective length is given as 24 feet. So now end conditions are not given, but the effective length is automatically available to you, 24 feet. And use ASTM A572 50 kg. So FY is 50. That means we can use these AISC tables. So the appropriate strategy here to find the lightest shape for each nominal size from column load tables, which are in 4.1 of AISC table, and we have explained it earlier also in the previous example how to use these tables, and also in the previous video lecture on design strength of column sections. And then we will choose the lightest of these. So based on those tables, we find these sections will be able to take this load of 190 kips, W8 by 58, W10 by 14. So values are more than 190. Any value less than 190 will not be acceptable. So we select these numbers. Now we find that out of these, if we see here, W10 by 49, because this 49 pound per foot, it is the lightest section and it can take 254 kips. You should also note that the load capacity is not proportional to the weight or cross-section area, because this is about critical load. Although the W8 by 58 has the smallest design strength of 4 choices, but it is the second heaviest, and the lightest is W10 by 49. Therefore, we will use W10 by 49, which is lightest W shape. Now, if there is another restriction in the question that use a W8 section, then you will be restricted to only this section. In that case, you will not use W10. So we have to take care of those considerations which are required due to some requirements of either architecture or some other service requirements for the structure. Now we look at another section, example 3. Here it is given, the load is given, and you can see the conditions of supports. Select the lightest W10 section. So here the section is limited as W10 section, made of steel grade 50 to resist a factor load of 600 kg. So factor load is given directly. Now in this case, you can see here this situation. Assume that the weak axis controls the buckling, that is your y-axis. So enter design table of AISC with Ky Ly equal to 9 foot, because here we have these values according to y-axis. So 9 foot is the length, effective length. Then select W10 by 54 with a capacity of 625 kip, which is greater than. So from that table, with a value of effective length equal to 9 foot, we selected W10 section, which is W10 by 54 with a capacity of 625, and it will be able to take this load of 600 kips from those table 4.1, which we have seen in the previous example also. So this section is okay according to the load. Now check strong axis buckling strength. So enter the table for W10 by 54. Now we have selected this, so we will check that how much load it can take. So W10 by 54 with KL equivalent. Here you have to find equivalent value for KL, as you have seen in the previous chapter how to find KL equivalent from KLX. This value will be 10.53 and the capacity is 595.8 kips. We have to do this interpolation because that value in the table is given for 10 feet and 11 feet. By interpolation we get this value is 595.8. That means it is not controlling, it is not governing. Therefore what we have to do, we have to go to another section, W10 by 60 with a capacity of 698 kips for KY Ly. This is effective length with reference to y-axis equal to 9 foot and capacity is 666. So we have to restrict our effective length as 9 foot and check another section which is higher than W10 by 54. So we go to W10 by 60, which gives you a capacity of 698, and then we check again the same thing. We calculate KL equivalent, right, which is 10.5, and then by interpolation we get the capacity of this W10 by 60 as 666 kips. Now this value is more than 600 kips. Now you will find sometimes that the sections are not available in the AISC tables. So in that case if you are doing the design for sections which are not from column load tables, what you have to do, we will discuss here. So for shapes not in the column load tables, because as I mentioned, these are some limited shapes and the limited value of Fy, a trial and error approach is to be used, as you have seen in the other chapters of tension member or beam design. The general procedure is to assume a shape and then compute its design strength. If the strength is too small or unsafe or too large, it will be uneconomical. Another trial must be made by following the same steps. A systematic approach to make the trial selection is as follows. First step is to calculate the factor load Pu based on the values of dead load and live load. We have seen in the previous example and also in the previous lecture how to find the design load, because the load factors will be 1.2 times, and similarly for live load it will be 1.6, 1.2 for dead load and 1.6 for live load. Then assume a value for the critical buckling stress, because you don't know the value of critical stress, but that value which you are assuming should be less than Fy. Fy will be known to you, so you should not select the value of critical stress more than Fy, it should be less than Fy. From the requirement that phi CPN is greater than Pu, so your nominal strength should be greater than or equal to Pu. Now you know that this value for Pn is nothing but gross area multiplied by the critical stress. So in place of Pn we can substitute here gross area into FCR should be greater than Pu. Therefore we can calculate the gross area from here as Pu upon phi C FCR. So we will look for this gross area of the section from the steel sections table. We will select a section that satisfies this area requirement. So we will select first the section which will be not less than this gross area. Then based on that section we will compute the values for FCR and phi CPN for the trial shape. Revise if necessary if the value of FCR or this phi CPN is sufficient, it is more than the Pu value, that means design is safe, otherwise you will repeat the steps. So revise if necessary if the design strength is very close to the required value, the next tabulated size can be tried, otherwise repeat the entire procedure using the value of FCR found for the current trial shape as a value for step 1. Then we will check for the local stabilities, which is for lambda value, width to thickness ratios, and then revise if necessary if it is not satisfying that stability criteria. Here are these tables. So we are familiar with these tables here, different sections. So we will be using these sections for design. So those shapes we can use as in the previous example also. This is useful table which will be there. This table can be used only in this situation here. When you have to compute FCR and phi C Pn. So you have to reach up to this, select a section. Once you select a section, then you can make use of these tables for one, these different tables. Otherwise you will use equations 3.2 or 3.3. Select a W18 shape of A36 steel that can resist a factor load of 1054 kgs. The effective length KL is 26 feet. So effective length is given directly. So try FCR equal to 24 KSI, because that value should be less than this steel grade 36. So we have taken a value 2/3 of Fy. This is a good approximation. Otherwise you have a choice, you can take any other value less than 36. And based on this value, we calculate the value of gross area. PU is given here, factor load divided by phi C FCR. Phi C will be 0.9, and we substitute here the critical stress. That gives you a value of gross area 48.8. Now based on this gross area, you have to select a section from steel sections table. You can see here. So from this steel sections table, according to that gross area, which is 48.8, we will select this section which has area not less than this. So W18 by 192, because it is restricted as W18. So we'll go to the table of W18 shapes. So we select W18 by 192. So AG is 56.4 inches square from the table, which is more than the required. So we select this, and based on this we find the value of KL by R. Now value of R minimum will be taken again from this table. You can see here RXX, RYY, whichever is minimum, we will take those values and calculate slenderness ratio and check that it should be less than 200. So this will be first step to check. Now based on this we will calculate the value of FE. So we are using direct LRFD approach. Find the value of FE, phi square E over KL by R square. Substitute this value in the formula. This is what we have done in the previous lecture also, to find design strength by using LRFD equations, that is equation 3.2 and 3.3. This comes out to be 22.9 KSI. Now you check that this value of FE is greater than 0.44 FY. So we have to use LRFD equation 3.2. We come to that equation. FCR is equal to 0.658 Fy upon Fy. For this approach, for finding the design strength, please refer to the previous lecture for design strength of the steel column. So FCR we calculate in this way, substituting the values, and this gives you a value of 18.64 KSI. So we find phi CPN, because this is FCR multiplied by the values of phi C and the gross area. We substitute here, and this value comes out to be 943, but this is less than 1054 because the required design load is 1054. That means it is not safe. Now this value of phi CPN, which we are calculating by this equation 3.2, which is direct approach of LRFD, you can also find this value from table 4.1, because your section is decided. You have this section W18 by 192, and you can find the value of effective length KL, which you can find from this formula. KL will be equal to 118.8 multiplied by R. So that will be also another approach which I have explained in the previous example, to use column load tables. Now once we find that this is not the governing section, it is not able to take this load as its strength is less than 1054 kip, we try another FCR value. Now we can start with this section, because this section is now 943. We know that it will take this value, so we start with this value of FCR 18.64. So the value just computed for W18 by 192. The required gross area will be PU upon this value which we have taken now, 1054 upon phi C 0.9, and FCR which we have taken now for this section, which is failed, and we get this value of gross area as 42.83. Now we try another section. Again we have to be restricted to W18 as it is given in the question, that the section should be W18. We cannot take any other section. So W18 by 234 is selected based on this 62.83 square inch. So based on this we select this section. AG is 68.8, which is more than 62.8. Now we again calculate KL by R minimum, the value for effective length, and this gives you a value of 109.5 divided by 2.85, which is R minimum that we are taking from the table. So once we check this slenderness ratio is okay, then we'll go to the next step to find FCR value by using those equation 3.2. Same procedure will be repeated as in the previous step. We will calculate FE, pi square E over KL by R square. That gives you FE equal to 23.87. Then we again find that this value of FE is greater than 0.44 Fy. Therefore, we will use equation 3.2, and then FCR will be calculated based on this equation 3.2, and this gives you a value of 19.15 KSI. Once you get this critical stress, we can find the critical load 5 CPN. 0.9 is the factor IC, and PN is gross area multiplied by FCR. We substitute here, and this value is coming out to be 1185, which is greater than the required load, the design load. That's why our section is safe. So this will be designed. Now we will check whether this shape is satisfying this criteria, which is for local working. Because this shape is not in the tabulated table, so the width to thickness ratio must be checked. So we have to find BF upon 2TF equal to 2.8, which should be less than this, and we check that this is less than 15.8. This is the criteria. As you have seen in the previous lecture, we discussed the criteria for stability. So BF upon 2TF, we calculate the value, and then we found that this value is less than this number, 95 upon square root 36. Then H upon TW, we calculate the value of H upon TW from the table, which is given, and we found that 253 by root 36, which is 42.2. So then we use a W18 by 234 section. With this, we complete this example, and I hope these examples for design of column will help you to design different types of steel columns.